if we have, let's just move that over there. If we have, looking at this t-table, okay, this specifically is going to look very, very, very similar. The one that we'll be using on quizzes and tests that I'll post online for you will look very similar to what's described in the notes. It is essentially just flipped from the one in the book. The notes are describing the one in the book. And so you have a few things, as I mentioned earlier. You have that the column concerning the degrees of freedom, which will be determined by n-1. Okay. We have the two rows dedicated to the one-sided versus two-sided p-value. Okay. You'll see that they start at 0.25. And 0.5. We have this row dedicated to z star value, so we can ignore this. Okay. We have the confidence levels on top. This is going to be useful for finding T star for confidence intervals, just abbreviated with that CI apostrophe S. Okay. And what's probably the most important right here is we're going to end up finding the area to the right instead of the left. To the right of our test statistic. Okay. And this is just indicated by the upper part of the tail in our textbook. And its tail area is that 1 minus c divided by 2. You can also think about it as that alpha over 2. This of our test statistic, that to the right of our test statistic. Okay, those are kind of the key things you need to note about our table. The specific thing is we're not going to the left anymore, we're going to the right. You should also note that the highest probability we can get then, without multiplying by 2, is that 0.25, right? And it's given by our table. You're looking at that one-sided p-value at the bottom, where it says 0.25. Okay. So, we're going to end up using all these characteristics sans the z star value when we're working with any instance of a t-distribution. Okay. So let's get started on an example. Okay. So example starts saying that the National Center for Health Statistics reports that the systolic blood pressure for males 25 to 32 years of age has mean 128. Okay. So we're being given, just keeping track of what we're given, being given some official belief of mu, right? We don't actually know what mu is, we're just given some estimate by some official sounding institution, or there's some estimate people are willing to believe as a social standard, okay? Something plausible. We could pick anything, but we're just going to pick something plausible. Okay. And now, Calvi, being an industrious beagle, looks at the medical records of 16 executives in this age group to potentially find Rebecca a suitable partner. And she, being Calvi finds the mean systolic blood pressure in a sample, okay, of 16 executives of 124.552. Okay. So we have that we have an x bar. That's 124.552. And she found a sample standard deviation, so let's just keep that in mind. We're always going to have to know if it's a standard deviation or a sample standard deviation, or if she computes the standard deviation, something that alludes to either being theoretical or a standard, or a sample, something computed. So this is our key giveaway right here, but we're using a t-test. The key giveaway being the sample standard deviation business. Okay. And the sample standard deviation is going to be equal to 12. So the question then is, did Calby find evidence that executives have a lower mean systolic blood pressure at the level alpha is equal to 0.05? Okay. So we also have the alpha 0.05. That's nice, right? We don't have to check at all levels of alpha. Okay. And so let's start really looking at this problem. Okay. So to use a t-test, other than the fact that we're talking about a t-test, the fact that we're given the sample standard deviation is that key giveaway, right? And then we need to start looking at what our null and our alternative hypotheses are going to look like, right? I'm going to use HA. You can also see H1, right? I'm just going to use HA, right? And so we have some official belief of mu, right? So we have that the belief that mu is equal to 128, right? This is just some belief, right? Center for National Health Statistics reports this. Why not believe them, right? Okay, it's something plausible. And now, if you look at this, it's this guiding question of what we want to know, right here, this. Did Calby find evidence that executive means have a lower mean systolic blood pressure at the level alpha equals 0.05? So lower. So we're thinking specifically about, we're trying to find, so this is our alternative hypothesis, what we think, right? That the mean might actually be lower than 128. So notice that we're not done here yet, okay? We've just kind of scaffolded some stuff, okay? What our alternative hypothesis is going to do is it's going to inform how we construct this null hypothesis. So instead of this equal to, right, this mu is equal to 128, that's what we're going to end up using as our null hypothesis, but what our as our mu naught value, but what our null hypothesis is going to be is that the mu is going to be greater than or equal to 128. Okay. You could be nitpicky and say that it's equal to 128, but our alternative hypothesis is being guided by this less than 128. But for convenience, as it won't actually change the mathematics, you want to think about this kind of crux value right here. That if we draw a number line, we have this 128. We could test at 129, at 130, so on and so forth. But the strongest the argument for the opposition could ever be is 128. And because we're just wondering if it's lower. So the strongest argument could ever be is 128. So why not just pick worst case scenario, that it actually is 128. So this tells us that we're going to let mu naught be 128. Okay? And unless we're dealing with testing for proportions, it's pretty much usually going to be informed by data or by something of common sense. Oh, sorry, I'm getting a little tired there. And so now we go about doing a t-test, okay? So if you check our null and our alternative hypotheses, check out, okay? So consequently, we compute our t-statistic, right? And this is not surprising, right? We get this 128. We get our x bar, we get our s, we get our n. Let's change that. Let's change, oh, sorry about that. Let me just, we have this x bar, we have minus mu naught. We have the s over root n, okay? And then plugging in our values, right? We've got that x is 124.55, we've got that mu naught. It's going to be 128, right? We've got that S value, right, that was given to us right here, 12. And we've got that N, which if we look back here, forgot to write it down. Sorry about that. We've got that N of 16 individuals. We've got square root of 16, right? And just using a calculator and rounding to the hundredths, we find that this is negative 1.25. Okay. So why don't you just go ahead and pause the video here, make sure that you kind of know what's going on, because I'm about to wrap up the rest of the example. So if you're not following something so far, you should probably pause the video, write down your questions, see if you can answer them, okay? So we got our test statistic of t being equal to negative 1.25, negative 1.25, right? And as before, determining whether or not we're going to use a one-sided or two-sided t-test is going to be really, really crucial here. And so, because our alternative hypothesis is only asking if we have a lower mean systolic blood pressure, what we're going to use is a one-sided test. So the test is one-sided. Okay. Okay. So that's something that's crucial. The next thing, we need to determine if this data is statistically significant. So the next thing is going to be, we look at the t-table. If you look at the one in the back of your book, you'll see confidence level. Okay. See like 50%. All the way to 99.9%. You'll see, I'm just going to abbreviate degrees of freedom for DF. Okay. 1, 2, dot, 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 dot. I'm going to include 16, I'm going to include 15 and 16, dot, 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 dot. This goes all the way to 1,000. You'll see, let me see if I can, oh, there we go. You'll then also see that this thing does that Z star value, right? But we're ignoring that. You'll see I'm just going to put 1S for one-sided p-value. I'm going to put 2S for two-sided p-value. And again, the table I'm uploading to Canvas, actually the class website, sorry about that. Table I'm uploading to the class website, confidence level will be down here, and the p-values will be up here. So they'll be switched. But you'll be able to use the table the same. And the key thing to know right here is that, as noted before, we only have t star values. It's going positive, okay? So that says that if we're working, let's say we're working on a t-distribution, okay? First thing we want to know is we want to note the degrees of freedom. Degrees of freedom, as mentioned earlier, let's see if this works out. Yeah, so as mentioned earlier, we're going to have n minus 1 degrees of freedom. So, n here, if you look above, I'll add it real quick, n is equal to 16. So, n is equal to 16 implies that our degrees of freedom is equal to n minus 1, which is equal to 16 minus 1, which is equal to 15. So, on our t-table, we're immediately only going to look at the section we're immediately only going to look at the section, the row that corresponds to 15 degrees of freedom, right? It's degrees of freedom, okay? Let's see what that does. Perfect, okay? And then we're going to look for values. When you see values here, in the middle of this table, I'm just going to write values. Okay. You'll see, say, like 318.3. Let's actually under the 99.9% on the top, you'll see 636.6. You'll see 31.6. You'll see 12.92. You'll see other values, right? See like 3.551. 3.4966. You'll see other values, okay? And these are all test statistic values. Test statistic values, not probabilities. And the reason I'm emphasizing this is on a z-score table, the inside were probabilities, and the z-score values were on the outside. However, now the t test statistic values are on the inside, and the probabilities are actually right here in this one-sided or two-sided p-value portion. So probabilities. And this is because as the degrees of freedom change, so as degrees of freedom change, the t distribution also changes. Okay. Right, so I'm just going to say that one more time. As the degrees of freedom change, the t distribution changes. So that is a t of 10 is different than a t of 9 or t 11. They're very, very, very different distributions. So when you change your degrees of freedom, you're changing what distribution you're working on. And you can even see, if you look at the test statistic values, if you look at some of the example values I wrote right here. Okay, look at some of the example values. Some of them are really, really big, and some of them are really, really small. And that's because these degrees of freedom are allowing, essentially, they're changing the entire distribution. Okay. So we go here, got our degrees of freedom, and we had our value. I'm just going to put this right here in the center. We had that t was equal to negative 1.25. What that tells us is this would be a negative t star. And our null hypothesis was one-sided, right? If you look, our null hypothesis, let me underline that here, was them having lower value. So we're looking for this area. But our t-table gives probabilities to the right, not the left. And all values for t are positive. So we've got a lot going on. But really what it's boiling down to is we're just going to use the table differently. We just have to read the table. The actual in mathematics, if you look, is the same, right? So we'll calculation, get the t-table, we have our null hypothesis, our alternative hypothesis. Still the same thing we've been doing, okay? But it does pose this problem of we have this negative value. So what to do? So what we're going to do is we're going to deal with the absolute value. Because we know that if this thing is symmetric, which it is for our cases, we can take, here I'll go down just a little more. Let me erase this. I'll just redraw real quick. This again. Okay. This is negative t. By symmetry, we can find the absolute value of t. Right? Negative absolute value, positive absolute value. And if our alternative hypothesis is looking to the left, we can now just find, by symmetry, area to the right. So that means we're going to deal with t equal to 1.25. Find the probability of x, our random variable, being greater than or equal to 1.25. How we're going to deal with this is we'll look at our t-tables, and if you look at the one in the back of your book, and you go to the row that says degrees of freedom 15, and you go to the right, you're looking through all these values, and you start seeing values, you start seeing 0.691, 0.866, 0.074, 0.1341. So what we found is that we found a 1.074, and we found a 1.341. The table skips right over this 1.25. So what we know then, we can go down, and we can look at the one-sided and two-sided p. Look at the one-sided p, and we see that this one-sided p corresponding to 1.074 is 0.15. And we look right next to it, and we find that the one-sided p-value corresponding to 0.1341 is 0.1 or 0.10, however you want to read it, okay? And because our test was one-sided, we're going to deal with this one-sided value. But if you look below, you can see that the two-sided p-value is just this multiplied by 2. This would be 0.3. This is just 0.2, or 0.20, 0.30. Okay, however you'd like to read it. And so, the conclusion for our test, because our t value, the absolute value of this thing, is between these two probability values, we know that our p-value is between, we don't know exactly what it is, we know it's neither of these numbers exactly, we just know specifically that it's between 0.1 and 0.15. So I always like to take what is the worst case. So where alpha equals 0.05 is the significance level we're testing at. But we know that the p-value is between 0.1 and 0.15. So this means that in either case, we know that alpha is definitely going to be less than 0.1, and we know that alpha is definitely less than 0.15. It's less than both of these. But we wanted p to be less than alpha in order for this to be significant. So we conclude that even though we don't know the exact value of p, we only know some interval, we conclude that this is not significant. So conclusion, let me just erase some stuff here. Okay. Conclusion, the data is not significant. Okay. So all we've done, really, is we've really just done the same process, just with a different table.